Perfect. Uh, Today we have Iury Simoes-Sousa from Woods Hole Oceanographic Institution. He is a postdoc and he's actually based in San Diego. Um, he's going to talk today about the May 2024 flood disaster in southern Brazil. So giving us a perspective on air sea water fluxes. So go for it, Iury.
Hello, everyone. It's a pleasure to be here giving this presentation. This is a paper that we worked together with different colleagues in different institutions, and also we're gonna talk about SWOT. And so, just to give a sense a little bit on what kind of research that I've been doing, I'm an oceanographer, and most of the time of my research has been focused on ocean small scales and how it upscale to global scales. And so I have experience with mesoscale and submesoscale dynamics and biophysical interactions at these scales. But since I started at Woods Hole, I wanted to also do the opposite path and study how global change could lead to local impacts. And so this is today I'm going to present one of these projects that I've been working on. But to give a context, we are facing a new era of the ocean surface height data, and so you probably have heard of SWOT mission and how it's giving unprecedented sea level height, and so this is an example of what we had before with the interpolated fields from Aviso, from the constellation of Nadir altimetry that we have until now. And this is an example of how such a high resolution sea surface height that is provided by SWOT. And so this has been not only revolutionary for oceanography, but also for hydrology, as I'm going to show during this presentation. And I was actually working on a different project. This is a work that I'm collaborating with my supervisor, Tom Farrar, and we were actually working on this problem that we have these gigantic icebergs that are detaching from Antarctica and interacting with seamounts and capsizing and generating these mini tsunamis. And this is very cool. It looks like just throwing a rock in a pond, but in a very large scale. And we can see that from SWOT as those snapshots. And this is another example of such a snapshot, and we can look at the sigma naught, which shows the backscatter from the satellite. That you can even see the iceberg there, and you can see the radiating waves from the capsizing event. And there are some very interesting analysis that we were doing for that. Like for example, we can solve the equations and restore the time at which we had the impact. And another interesting thing is that we are seeing that we were expecting the waves to basically just radiate, and we are seeing that, but we also see some waves very close to the icebergs that can be related to the volume and the bobbing of the iceberg. So there is a lot of interesting physics that can be extracted from an analysis like this. So I was doing this, but then it happened what we can call the greatest climate disaster in Brazil's history, which happened in the South Brazil. These are some of the images of the city of Porto Alegre, the capital of the state, and the amount of destruction that happened. There was in May last year. So it was a 9-day event. But some of the consequences of this event is still lasting to today. We actually had the local airport only opening this year, reopening this year. And so to give a sense, 70% of the municipalities declared state of emergency. We had 2.3 million people that were somehow affected by these floods. So to give a sense about the large-scale atmosphere conditions, here I'm showing the average temperature anomalies, water vapor anomaly, height at 500 hectopascal, and the average precipitation during the duration of the event. And in yellow, I'm showing the polygon that represents the Rio Grande do Sul state. The hatches here, it was very tricky to obtain because we had to select the same time of the year for all the years that we had from Mera to, for example, and we resort to a cloud service to do this analysis. So these diagonal hatches are values above the 90th percentile, and the cross hatches are values below the 10th percentile of the distribution. And so we can see here is that we had an extreme heat wave happening in the central South America, which is 6 degrees above the median and lasted for 10 days. And this is accompanied by a cold front that was coming from the south. At the same time, we had a moisture transport that is being brought from the Amazon region to the region of study by the South American low-level jet. So this is a known feature in the region. But what we had that was unique was a combination of these factors with an atmospheric blocking event. So here we are showing the red polygon here. It's a criterion for identifying atmospheric blocking events. They are defined by how long these anomalies are staying in that place. And so it shows that this anticyclone was basically stalling the cold front to propagate and concentrating consequently concentrating the rain in a very localized place. So when we are talking about these atmospheric blocking events, we actually found a very interesting paper by Rodrigues and colleagues at Nature Geoscience that describes that these blocking events in the region are triggered by the deep convection initiated by MJO, which excites a Rossby wave train that propagates all the way to South America. And these events, what is very interesting is that for their analysis, most of these events happen in the beginning of the year during the summer. And this actually leads to marine heat waves and droughts in the region. And what we are seeing here is that we probably had a different outcome because this event was happening in May when MJO is further north, and so that could explain why you could have a different side effect of an atmospheric blocking event like this. All right, so we also analyzed the extreme events and some of the contributing factors, and here I'm showing all the meteorological stations that we have in the region. And the colors in the background are values from IMERG. And so this is the total rain that happened during that 9-day event. And what we are seeing here is that, so this is for the panel A. Panel B here is showing the time series of extreme events. And so we are basically just taking events that lasted for at least 3 days. And we are averaging the rain the total rainfall from these events for a very long window. And these dots here are the events that are above the 90th percentile. So these are the outliers of the extreme events, and they seem to group during El Nino years. And so we can clearly see that there is an effect of the El Nino in the region in terms of intensity of the rain. And when we look at the monthly precipitation anomaly, this is a composite of the monthly precipitation anomaly for each month of the year and each ENSO index. We can see that El Nino years tend to make to rain more in the region, and their influence is even stronger than La Nina years. And so we can clearly see that there is an influence of ENSO in the precipitation in the region. But when we look at the time series, we didn't have any event like this since the 60s. And so it doesn't explain by itself this extreme event. So it's probably a combination of factors that I explained before with the fact that we were in a El Nino year. So this is a view from space for before the event. Now we are focusing in the metropolitan region of Porto Alegre, which is the capital of the state. And I'm giving some references here. We have an encounter of different river channels that encounter to generate the Guaíba River, which is actually connected to a very large lagoon called Lagoa dos Patos. And so when we are looking at the image for before the event, that's how it looks like. And at the peak of the event, that's how it looks like. And so we can clearly see how extensive was this flood, how it affected the croplands in the region, but also the urban areas, mostly in the north part of Porto Alegre and also the metropolitan region. And this is very interesting, but this is what it was for us to do such analysis before SWOT, because this is giving us a good sense about the lateral distribution, but not much about the depth of these floods. And so if we use SWOT, and here I'm using the pixel cloud data, which is each pixel is 5 by 5 pixels. We aggregated the pixels by applying some filters, and we could combine that with the data that we had locally to have a time series like this. And so the two lines here are the two gauge stations that I actually forgot to mention, but these are the two stars here that I'm presenting. So the red one is further upstream, and the blue is downstream. And we can even see here, well, there are many things to tell about this graph, but it's a huge jump in the water level that we had in a very short time. And also we can even see some gradient between the two gauge stations, which is very interesting, and it tells us, it gives us a sense about the intensity of the currents that are derived from the flood. And the stars here are the values that we are obtaining from SWOT. And so we are averaging around each of these stations and presenting the values here. And so there are a couple of things that I want to mention. One is that we were very lucky to have SWOT right at the peak, because SWOT has, now we are in the science orbit and has about 21 days of repeat orbit. And we were very lucky to have both SWOT and also Landsat, and that's the image that I showed before, right at the peak of the flood. And if we use that, and if we combine with a digital elevation model, and here we are using the FABDEM. So the FABDEM, it's a digital elevation model that takes into account they use a machine learning method to extract and remove the effect of buildings and trees. And we realized that it was way better and appropriate for the region than other digital elevation models. And if we combine that, so we have the water surface and we have the topography, we can map the flood water depth in the region. So this is a snapshot for before, and this is a snapshot for at the peak of the event. And so we can see here the distribution of the water depth, that it's not only dependent on the topography, but also on the gradients of the water surface, that it's very clear that it's present in this region, because we can see from the two gauge stations. And so this is a kind of information that is very important for example, engineering applications, for mitigation strategies, and even evacuation of populations, and also to inform flood models to develop better flood models for the region. And another thing that is very interesting about an analysis like this is that this is the first time that we can do such analysis with satellite data only. And this is very important, because many places in the world is not like this, that we have gauge stations in the region. And it's also important for us to check how the flood water was distributed and how it could inform the different strategies. We can also estimate the total volume of this flood, and just for this region, this is 1.5 billion cubic meters, which is enough to supply New York City for more than a year. And this is a only 9-day event. And so it's pretty striking how this event was intense and disastrous. So since climate is not an isolated issue, we also investigated the flood impacts. And here I'm presenting results for the land impact. Here we see that 54% of the croplands in the region were affected. These are mainly rice plains. And what is interesting is that to mention is that these rice plains are not only consumed locally, but exported to other regions. So it shows how an extreme event like this, it has far-reaching impacts. We also had 25% of the urban areas that were flooded. The vegetation damage here index that we are showing, it's showing that we had severe disturbance in wetlands, croplands, and grasslands, and some of these regions, it's clear that it have affected the local ecosystem. And this flood, as you saw from the images, is not only it was very heavy in sediments, and so we had there are other impacts that we can see in the vegetation in the region. We had urban areas affected, of course, and so here what I'm showing is we are combining the extension of the flood that we had, the map, and with social vulnerability index, and here what we are seeing is that 67,000 people in social vulnerability might have been impacted by this flood, which is about 16% of the total affected. But this is also the least less resilient population of the region. So it highlights how extreme events can exacerbate social disparities, particularly in the global south. So one of the co-authors of this paper is Agatha, and Agatha was, well, she's now at Scripps working with Sarah Giddings on this work, and it always started with a question, because she came in and said, well, this is a flood that it's occurring upstream. What happened when it arrives at the coast? So what about the river plume? And so here it's a snapshot from true color image of one of the plumes that were generated by this flood. And when we look at SWOT, this is the sigma naught. So it's pretty impressive how it could basically mark the structure of the plume and even the front of the plume. There are some questions that we have, for example, and maybe someone could give a feedback, but like we are very intrigued with this very low signal at the front, because since these are gravity currents, we would expect to have convergence at the front and hence increased sigma naught. But there is a lot that can be done with that. But SWOT also have the water surface elevation, and so and I mean the sea surface height, so the barotropic component of river plumes, it's called the Holy Grail. I mean, it's very hard to measure with observational studies, and we didn't have until now, we didn't have the opportunity to observe that from satellite. And what we can see is that it's clearly, well, it's very noisy, but we can still clearly see the boundaries of the plume and the gradients related to the plume. And if we make a cross section here, we can see that there is a clear trend related to the barotropic component, and even some signal that it might be related to the front itself. So there is a lot that we are doing right now. We are not sure if we can see the liftoff, for example, and how to filter out the noise in the best way to take into account the structure that we are seeing from the sigma naught. So one of the things that we observed is that it's very tricky to guess when, well, it's predictable, but tricky to guess if SWOT has observed or will observe such an event. And so we created this tool. It's an online tool that anyone can run that basically can predict when SWOT is passing, what is the pass number and the cycle number, which can help you to access and download the data that you need. And we have colleagues that have used that to combine measurements in the Bay of Bengal, for example, and other regions too. So we are also doing the same analysis for coastal floods in US. So this is an example for Mobile area, and this is a flood that was related to the Helene storm. What I'm showing here, it's a similar analysis that I did for the floods in Brazil. So it's showing the water depth anomaly, and here it's a time series of the water level in the region from a gauge station. This is another example for the Alabama port in Dauphin Island. So you can really see the details of the flooded areas that you will not be able to see before SWOT. And this is not only for extreme events. So this is an example for the tidal floods in the Chatham County wetlands in Savannah. And this is just a tidal flood. And we can still see the flooded areas and estimate the distribution of the flooded area, flood water, which is very important for other applications. So we are also trying to expand this method to the raster product. And so this is an example of the analysis with the pixel cloud without any smoothing. And we can get a very similar result from the raster, the 100-meter raster, which is way easier to work with. Of course, there are some differences that we notice in different regions, and also right now this is a work in progress, and we also have to combine better the different tiles from the raster product. But some of these differences are basically related to the filters that we are using and how they could be comparable to the filters that we are using for the pixel cloud data. So some of the analysis that I'm doing here, it's with very large data sets, and we have a projection for the Earth Science Data Archive for 600 petabytes by 2029, and this is very massive. And if you're just like me and have no sense about 600 petabytes mean, I did some back of the envelope calculation here, which sums that 600 petabytes will be around 15 million Finding Nemo movies, and if you're really fan of this movie, it would take you 3,000 years to watch with no pauses. So it's a very massive data, and how to deal with all this data set. So there are different ways that we can deal with that. We can develop better data streaming and cloud services that we can access this data and deal with a more in a way that can be more integrated with systems that we need this data, such as data assimilation. But also we have machine learning methods, which is one of the answers. So we have supervised methods that can fill gaps, make predictions, emulate the physics that it's not by taking into account the data. But also we have unsupervised methods that can construct the latent space and compress the information that is in this data by organizing patterns and exploring the relationships in the hidden structure. And so this is an example from a colleague, Xavier Prochaska, that they were doing a similar analysis, contrastive learning for SST gradients, and we are grouping here SST gradients by the patterns, and we can see how the different groups, I mean the level of detail, it's separated in different regions of the latent space. And so this is very important for many other applications, such as you can understand trajectories in this latent space, but also understand how different groups occur in different parts of the planet. So I think that my research is being a lot inspired by the Earth and Climate Science to Action. And so I would just try to connect here some of the research that I've been doing, but the idea is to develop a research that is transforming scientific insights into practical solutions for environmental and societal challenges. And that goes from the foundational knowledge to an applied research, but also, research that it's focused on the solutions of community problems and also public understanding and exchange. And I think that this is, I think that as a community, we should do more things like that. Although I think that I still want to do more pure science and foundational knowledge research, but I think that as a community, we need to get more close to the society. And this is a vision of an open source science. And so the earth sciences or the oceanography, it's bringing the questions, where the computational sciences is bringing the tools, and that it's what we could call the computational earth science or computational oceanography. And this is not only about a science that is reproducible, but also accessible and inclusive. And so just to finalize this presentation, I want to give a citation from Ailton Krenak, which is an indigenous philosopher and leader in Brazil. And he says that we need to be critical of this imposed notion of homogeneous humanity. And just like if you want to map a 3D object, you need different point of views. And so diverse of perspectives across disciplines, backgrounds, and cultures is essential to tackling the complex earth and environmental challenges of this century. So without further ado, I'd like to thank you very much for the invitation, and I'm open for questions.
Well, thank you so much. And questions for Iury? Maybe I'll start with just a really quick technical question. When you showed the plume map over the ocean, what resolution SWOT data were you using?
Yeah, we are using the level 3 250, so it's meters, so it's the unsmoothed product. And we are also removing, since we don't know very much if the tidal corrections are very good for very close to the coast, and so we are basically putting it back and analyzing the results from that. We didn't see much difference though, and so probably because the spatial scale of the differences are way larger than the plume itself. Yeah.
Thank you.
Yeah.
Other questions? I guess I'm also curious about oh, I see Ryan has a hand up, so let other people go ahead. Ryan.
Thanks. I also have a slightly technical question because I also don't know anything about rivers. So when you showed the water depth data, right, from what I understand, SWOT can just see the elevation of the top. But where's the information of the topography, the actual ground topography comes from?
Yeah, so we are not using the right now. We are not using. So wait, you're talking about the plume part, right? So we
No,
at that time
the actual flood one. But
yeah, the flood.
But, okay,
yeah, so we are using. So for the flood, we are using the FAB dam to get the topography, and so basically, I mean, we only have the topography for places that are not that were flooded, and so it was not water before the flooding, and so it basically just showing us the flood water depth distribution. And so when it's above when in the areas that we had water before, it's basically just showing the anomaly over the mean level. Yeah. Hi, Andy.
Hey, Iury, that was a great presentation. Thanks so much. I was gonna ask a higher order level. I mean, what's really nice here is that you're sort of working at the interface between the oceanography groups that are thinking about SWOT data and the hydrology groups. And I was wondering if you could say a little bit more where you think you see synergy, where we could be working together a bit better, especially just coming from the SWOT meeting last week.
Yeah, I think that there is a lot to be done, and I think that there is some overlap with the HR and coastal areas that could be used for that. And I know that Sarah Giddings' group is doing that. We are, they're using the HR to understand, how the tides vary inside these two areas and how you could extract them to obtain other coastal and estuarine processes. And so I think that there is a lot that can be done. I think that some of the challenges is that the processing is very different for the HR and the LR products, and some of the corrections we don't want, and some of the corrections we want to get from the LR and apply on that. And so and so far we don't have a coastal product for SWOT, and so that could be another thing that can be done. And one thing that I can also mention is that the availability of the HR product depends a lot on the orientation of the coast related to the orientation of the swath. Because if you have if you have a long coast swath, you're gonna have more HR data than if you have a cross coast swath, because they basically just cut right at the coast, so it will be flagged that it's oceanography. And so I think that there is a lot of challenging in the jargons too and the language too that can be done. But I think that it's very important to do because I mean, these are two separate teams, but there is a lot that can be done in the coast in terms of ocean dynamics that SWOT can provide. Yeah, and so and also as we can see from the example of the flood in Brazil, a lot of what is happening in the coast depends on what is happening in land, and so this is another reason why it's so important for us to do these synergies.
Yeah, that's really helpful. Thanks.
Other questions? Maybe to continue that thread, it was really interesting to see the flooded areas. And you mentioned that rice paddies or rice growing areas tend to be flooded. Rice is known to be grown in sort of areas that are floodable. So presumably those areas in the estuary that are floodable were chosen for rice paddies, and that's an intrinsic vulnerability. But what are the implications for
so the implications is, so if we look at the images, there's a lot of sediment and mud that is being carried by this flood. And so it's not only that you're basically changing the topography of the region, because now maybe some of these places might not be flooded anymore, and you have to drag them and restore the elevation that you had before, and so they basically lost most of the crops that they had before, because it was all now under the mud. And so so I think that this is most of the consequences, not only the water, but what the water is bringing. And also, I think that there is also, I mean, it's very unknown what other pollution and contamination that was brought from this flood water that was being carried all the way from the watershed upstream. And so I think that, so I understand that maybe the way that we present as, well, croplands, their rice plains were flooded, and well, this is expected. But I think that for an extreme flood like this, we have to pay more attention to what it's being brought from the water.
Yeah, presumably the rice plains are sort of a built environment because they have dikes, they have to be floodable, but farmers are there because they assume they're going to be reproducible year after year.
Yeah.
One of the questions that comes up for flooding is about the built environment upstream and how that changes stream flow and channeling. And so I'm wondering, and you may not know the answer, but I'm wondering how much upstream changes might have affected the particular flooding in Porto Alegre where you were looking.
Yeah, so one of us, I don't know if that answered the questions, but some of the problems that we had was, we had dams that were completely destroyed by this flood, and they didn't work, and they didn't work as expected too. Some of the floodgates that we had in the city of Porto Alegre, because Porto Alegre is known for having floods. It's an encounter of rivers, but nothing like this. You can see from the time series of the extreme events that we didn't have anything like this. I think that the last very major flood was in the 40s, but it was not as intense as this one. And so I think that, we had some problems in terms of the engineering structure that was, made to contain these floods. And I think that there is a lot of discussion about what extreme levels we should take into account to make new constructions and reconstruct these floodgates and dams. And is this a new normal? We don't know. I mean, it's very unclear. I mean, the IPCC report shows that we have an expected increase in precipitation in this area, but it's very unclear about in terms of the extreme events like this, because at the same point that we were expecting to have more rain with climate change, we were not expecting to be that intense. And so I think that there is some work that can be done in terms of checking if this is something that should be the new normal, and how often events like this will be happening.
So Ryan has a hand up. Go ahead, Ryan.
Sorry, I keep interrupting you.
Don't worry.
So the preceding conversation kind of reminded me a part of your talk that I didn't understand very well. Is right, you kind of called this a climate disaster, but indeed it is very hard to actually tell if this is a climate-driven one or just by internal variability. I didn't really understand. Right, you kind of explained that the blocking could be driven by MJO and the Rossby waves, but the time, apparently the month is different. And what kind of do you think? What the climate of perhaps MJO change that kind of led to this? Sorry, I didn't really. Yeah, I was basically asking you to really explain that bit a bit.
No, I think this is a very good question, and to be honest, I don't know, and I think that it's something that it's a follow-up. It's a natural follow-up question for that problem, but very important question, and I think that there's some research that should be done to understand that, because as we can see from the time series, of course, I mean that the most of the atmospheric blocking events in the region happen in the beginning of the year, but not in May. And so that kind of shows that this might be related to climate change, because we were not expecting to an event like this happen at this time of the year. But at the same time, we don't know. I mean, maybe some past event that we had was related to that, and we didn't have data to check. And so I think that it's an open question, and probably we would have to understand a little bit more better about the mechanism of the generation of the brain of this extreme event.
So maybe I'll ask one more question. Because when you talk about a rain event like this, I think there's been a lot of work in California and the US West Coast to anticipate big rain events, which are usually classified as atmospheric river events, and to use that information to not just give out warnings so that people can say, oh, it's going to rain, but to manage water resources, to manage dams, to decide when to release water from dams. This concept of forecast-informed reservoir operations has been really important. And I guess that leads to questions for southern Brazil. What would be useful for a forecast? What's actually actionable information? And is it useful to think about these types of events in an atmospheric river framework? It doesn't seem like you're looking at the sort of filamented structure that people think about for California rainfall.
Yeah, I think that well, some of the elements that we have there, well, actually that kind of connects with what Ryan asked, because I forgot to mention about that. But those extreme heat waves, the heat waves are happening in Brazil. It's clearly becoming more frequent, and that was one of the key elements of the flood, and I think that. But some of these elements are already there. So we have this South American low-level jet that it's usually bringing humidity to the region, and this is actually important because it's a very productive region, as you could see from the cropland distribution. In terms of what kind of information, well, they had to compile some of these results and make a final report of the impacts of the flood. And but to be honest, I don't know. I think that I think that some of these analyses are good when you have an extreme event like this. But if you have a place, for example, that you didn't have an extreme event yet, you would have to rely to models, right? And so. But I think that when you have a data like this, you can basically inform the model and check and improve the flood models. And one of the things that I'm discussing with Tamlin is we are trying to create a global database of floods that are observable by SWOT. And that could, for example, help to improve flood models. And that could be used to, if we have for example, if we have an expected increasing precipitation and increasing extreme events in a region, even though we didn't have any of these events yet, we can use some of these examples to inform models and check how it would be an event like this if it happens in different places. So I think that it's a combination of examples that we can observe from SWOT and model simulations.
I guess you're alluding to something that you talked about machine learning and the large data, but machine learning techniques are typically not very good at getting extremes that are outside the training data. And
yeah,
it sounds like you're thinking about how to use cases from one geographic region to create training data that might help in other areas.
Yeah, of course. Yeah. And I think that there are ways also, I just went to Brown yesterday, and I actually gave the same, very similar talk there. And I was discussing with Baylor about how you could use emulators, for example, to accelerate the development and the usage of model simulations. And basically, of course, I mean, you can still use the emulator outside the training space. But you can always come back, and if you find something very different, you can always come back and run the numerical simulation to confirm those results. And so I think that the use of emulators, it's a very, it has a very high potential for exploring the latent space for in events and extreme events like this. And even creating very different versions of extreme events. For example, you can have Hurricane Sandy and vary the initial conditions and run thousands of simulations of the same event and check, how different parameters could change and explain the physics that led to the state that we had from the event. And so I think that there is a lot of potential to use big data analysis and machine learning for events like this.
Yeah, well, that's a nice thought to leave on, maybe. If there are no other questions, I'll pause a moment to see if there are, but if there are no other questions, thank you so much for a really great talk and stimulating discussion.
Thank you very much.